All right, electronegativity. So, electronegativity, the best way to explain it is probably thinking about electrons being like a Christmas present. If you have some valence electrons that are like a Christmas present and you put it between two children, or in our case, two atoms, what do you think is going to happen? Well, the answer is they're going to fight over it, right? Electronegativity just tells us who wins the fight. So if we look at the periodic table, we can see that as we go to this upper right corner, that tells us that our biggest bully in the entire table is going to be the fluorine atom. So there's nobody that can bully fluorine because its electronegativity is too high. So electronegativity is a way of determining which electrons are really shared and which ones aren't. So they are shared in quotation marks, but which atom actually owns the electrons a majority of the time, which atom is going to have those electrons around it a majority of the time, that's what electronegativity is really trying to tell us. So in a way, it's kind of like the bully system. The bigger the number, and the biggest number being 4.0, that's the stronger, more electronegative atom, or the biggest, meanest kind of bully. So our metals are pretty wimpy. Their electronegativity is pretty low, and that's because they want to get rid of electrons. They don't want to gain any electrons. But our non-metals are going to fight over them, and electronegativity tells us who wins. So when we think of electronegativity, we just have to think this is the first glimpse at non-metals trying to pretend to be like metals. So what we're seeing here with this generic structure is that if we have an atom that is electronegative, it's going to own the electrons most of the time. And if it owns negative electrons most of the time, notice we give it a partially negative charge. That's a delta letter, so it looks kind of like a D with a tail. And then you have a negative sign. So it's kind of D with a tail. That partial charge is exactly what it sounds like. It's about half of a real charge. But we're starting to see that even though we're not sharing very equally. And this tells you who the bully is. And it also tells you, kind of who the wimp is, for lack of a better term. And because atoms and molecules have partial positive and negative charges, those can attract other partial charges from other atoms. So if this is a partial positive, it can attract another partial negative. If this is a partial negative, it can attract another partial positive. And that's what holds the entire living world together. So if your headache has a negative active site, all you need is a positive receptor in order to bind to it to relieve those symptoms. So a lot of what we're going to see in upcoming chapters is this ability for positive and negative attractions to start forming weakly, but it's better than nothing. And that's how the human body works, by making partial charges from nonmetals, where otherwise there would be no charges whatsoever. So when we do electronegative kinds of problems, what we're really just doing is subtracting. We're looking at the electronegativity table, and then we're finding the number, subtracting it. And it doesn't matter what the subscript is. It doesn't matter how many atoms are there. It's a one atom to one atom calculation at a time. There is no multiplying or dividing, anything like that. Literally, we would go to the electronegativity table, which you're given on the exam. We would find for hydrogen that it's 2.1. We would find that if it's attached to another hydrogen at 2.1, the subtraction is 0. That is pure covalent, pure sharing, because there is no bully. And when we say that it has no difference, as long as it's going to be from, if it's going to stay less than 0.5 in electronegativity, that's what we call nonpolar as a bond. So anything that is less than 0.5 in electronegativity, again, that's a nonpolar kind of bond. That's different than if you're, say, 0.5 all the way up to, say, 2 in electronegativity. We would call those polar bonds. And those definitions we're going to use for at least 2 exams, both exam 2 and exam 3. So as we look at some of these polar bonds that they show here, notice they've labeled them polar covalent for being 0.9, 1.4, and 1.9. We're just telling you that 0.5 is kind of the line in the sand of where to make the distinction of not polar enough, so nonpolar. Because theoretically the only nonpolar bond is 0, but up to 0.49 you're still not enough polarity to matter, so we still consider you nonpolar overall. So if you find chlorine on the periodic table and look at its electronegativity, you're going to find that it's 3.0. Hydrogen still 2.1, so we see those. Chlorine's tied for the third biggest bully with nitrogen at 3.0, but nitrogen being a smaller atom, that electronegativity means more to a smaller atom than it does with one that has more electrons. Goes back to that parent in a mall with children kind of analogy. If you have 17 electrons, losing or gaining one isn't as big a deal as if you only have 7 in the case of nitrogen. So even though chlorine and nitrogen are both 3.0, nitrogen's 3.0 actually means more. The second biggest bully overall is oxygen at 3.5. And then the biggest bully of all is fluorine at 4.0. So doing the subtraction, you get 0.9, that's polar because it's larger than 0.5. 3.5 minus 2.1, superpolar. And then almost ionic is 1.9 because we're getting very close to that threshold of 2 where the bond's just going to break. It's going to form a positive and a negative ion, and you're going to be ionic, and that typically only happens with a metal. Because if you go back to your electronegativity table, their numbers a lot of times are below 1, especially on that left side of the periodic table. So your textbook uses 1.7. I don't really like that just because they just showed us an example of 1.9. But the take-home message here is 2 is a good indicator of what to expect because that 1.9 for HF is going to be in there. Anything above this, you're getting pretty close to being ionic. Anything below this is going to be covalent, so sharing. So after this kind of 2 threshold here, you're going to expect that bond to just break in 2. Somebody's going to get the electrons, somebody's going to lose the electrons, and that's exactly what happens with metals and nonmetals. But as long as we're in this kind of lower threshold, below 2, there's going to be sharing, albeit not much as we get close to 2. But when we get down here to 0.5, this 0.5 kind of increment down here, this is where we'd expect things to be nonpolar. Whereas this entire region from here to there, extending out to 2, this is what we consider to be polar. So polar molecules are strong. Things like water are very polar. But things like oil are very nonpolar. And this is why polar water, H2O, and nonpolar oil, things like methane, CH4, or even octane, which is a much larger hydrocarbon, they don't mix. And that's because if you're polar, you're going to have partial positives and partial negatives. If you're ionic, you have real positives and real negatives. If you're nonpolar, you don't really have anything. And that's what makes you very weak, in most cases gas-like, because you don't have any attractions to each other. So the reality of all these lectures for this chapter, kind of now full circle, is that strength is going in this direction. The stronger you are, the more charge you have. And now we're starting to see molecules have a little bit of charge. And that's kind of the take-home message of the introduction of electronegativity in this chapter. So again, try to remember those definitions. 0.5 is the dividing line for polarity. If you're 0.5 or larger, you can expect to be polar, all the way up to about 2 in electronegativity difference when you subtract those 2 values. And then if you're like a hydrocarbon where you're carbon to hydrogen, 2.5 to 2.1, it's just not going to be enough to be polar. So not going to be enough to mix or dissolve into water because you don't have any of those partial charges needed to interact with water. So here's those definitions in words. It's something to commit to memory just because we're going to see these in the next chapter and then all throughout the next 3 chapters as we approach exam 3. So it's a good sized chunk of exam 2, but it's a huge sized chunk of how we understand and develop ourselves into exam 3 over the next 3 chapters. So the rest of this chapter is all about names, and we'll pick that up in a separate video because there's a lot to learn there.